Okay. Hello once more. Today, because lots of time passed through our previous class, we will make a quick revision about what we discussed previously, the main ideas of direct current, and then we'll move to starting the beginning of alternating current, because the second part of semester will be about the sinusoidal alternating current and the using of method for calculations that we discussed previously for this type of energy sources and consumers. I mean, they are sinusoidal sources. But for now, let's start, as I said, about quick revision, what we were doing on all previous classes. We were discussing the direct current calculation because it is the simplest mathematical apparatus, the simplest approach for our disciplines, and it gives us opportunity to see the main ideas. What it was. It were 9 lectures. In our methodical books, you have this methodical book on your email. And starting from the basic definitions, what physical function we are using for describe electroenergetical system, and the main equations as Kirkov law and Ohm law, and the methods how to transform this equation in more simple way to solve some electrical tasks, to find currents, voltages, powers in our electrical system. So what it was starting from February and ending in May, and ending in the end of February on the starting lectures, it was about basic definitions, that all that we discuss in functions of voltage as a potential difference, as energetic characteristic between 2 points, what amount of energy we should use to move initial electrical charge, move electron from one point to another point in some conducting system. The second main function is current, the derivative of charge by time, the moving charge in some conduction medium, and the amount of this moving charge per time it was current, and the proportional function between them as resistivity. It was somewhere here. Here it is. The proportional function between them as resistivity in ohms that characterize any space, any conduction space that we are discussing in electrical system. This characteristic, this resistivity, could be linear or non-linear if independently on the value of current and on the value of voltage, if it stays the same as a constant, it's called linear, and the graph between current and voltage become a straight line. If the resistivity could change, for example, as a function of current or as a function of voltage, for example, some metal object, depending on the value of current, could hit on different value, the temperature will be different, and the conductivity depends from temperature. That is why the resistivity, the opposite value to conductivity of metal object, could vary from temperature. That is mean could vary from current. In this situation, if the resistivity isn't constant, we obtain the non-linear function of voltage and current. And the main equation that describes it, the Ohm law, and we are using it as one of the main equations in our electrical engineering cars. Then we could divide all elements that we have in our mathematical model. We are describing some electrical engineering system as a mathematical model of objects. All objects are material points. That is mean we neglect any spatial dimensions. We using starting from direct current. That is mean that we neglecting also any time dependencies. We are just talking about material points that are connected between each other. And all objects we could divide on sources of energy, two types of sources, voltage and current. Voltage source gives us constant voltage and current could change. The current source pointed this way. It gives us constant value of current, but the voltage could be any. For voltage source, the constant voltage. For current source, the constant current. And all other elements, they are named as consumer or load or passive elements. It is a combination of resistors and all energy that voltage and current sources produce. It consumes by resistors in different parts of our system. Also, then we were talking about the basic concepts, the basic topological elements inside our model. We discussed that the main elements in electrical circuits, which is combination of sources and consumers, combination of sources and resistors. The topological elements we will speak as branch, node, and mesh, because somehow we should describe electrical circle in some way. That is why we should use some topological names to describe it. And it will be branch, a combination of elements connected serial between each other, branch between any two points of connection. Then node as a point of connection, then node the point in which three or more branches are connected. For example, we are looking on the node 1 and see first, second, and third branch. And also loop or mesh as a closed path between elements. Mostly we are speaking about mesh, the smallest path, the smallest loop between branches which are connected in the circle. These are the main topological elements then we are using for describing the situation. Then depending on how many meshes do we have, we are using the mathematical approach, because if we have such called single mesh system only with one mesh, it means that we have only one current, only single current. And the mathematical approach will be the simplest. We will have only one function to find the value of this current. Then we have a multi-mesh system. If the number of meshes different, the number of meshes more than one, then it means that we will search for different functions. And we should solve the system of equation as many number as many currents we have inside it. Also, we were describing the opposite situations, the opposite value of, yeah, hello. We are just, now we are just making short revision of what we were speaking about, because we have a quite long break, almost a month. That is why today I'm just making a short overview of direct current methods and what we were discussing previously to use it in sinusoidal circuits when we will move further on our course. Then also we are making video record just to see the whole material, the whole picture, and if you miss something, you could see it independently just at home. Then, well, let's moving forward. We were discussing the different situation of loads, of resistors, depending on the value of ohmic resistivity of it. Generally, resistivity lays between infinity high value and zero value. And these two situations are boundary situations of all available values of resistivity. If we have 0 ohm situation, it named short circle. It could be represented just as a single wire with 0 resistance connected between 2 points. In this situation, the value of voltage became 0. And the opposite situation, infinity high ohmic resistivity, it means that we have infinity high resistivity between 2 points, or other words, these points are disconnected. It's called open circles, open circuit. All other situations lay between these 2 boundary points. Then we discussed the basic laws, which we will use in our course. It was the Ohm law that connects voltage and current and resistivity. It could be written in passive and active case. In passive case, we mean that we have branch without any source of energy, and active case that we have some source of energy inside it. The most general form of this equation could be written as it's shown here. We are summarizing all electromotive forces, all sources of energy that we have inside branch. We are summarizing depending on the direction, positive or negative. Also, we're summarizing all resistors that we have inside branch. It could be a couple of resistors in a single branch. The main criteria is that the current should be the same in all elements. That it means that they are connected in serial. And also, additionally to this Ohm law, we are using Kirkov's law. To Kirkov's law about current, that total current inside some point or total current inside some area should equal 0. All currents that inflow this area equals all current that outflow this area. And the same law about voltages, that total voltage inside closed loop equals 0. If we will move from the first point on any path and return to the same point, in any case, we will obtain 0 voltage. Or it could be rewritten that total number of sources, depending on the direction, equals the total number of consumers that are inside this single mesh. It was 3 main laws. Additionally to them, we are using power balance equation that gives us power where we identify it as a multiplication of current and voltage. For the consumer, power is always positive. It equals or multiplication of current and voltage, or if we will substitute the Ohm law in this equation, we will obtain square of current on the resistivity or square of voltage divide on resistivity for any consumer. For the sources, there are 2 situations depending or positive or negative source value we have. If the current and voltage directions are the same, we will get positive power. If current is opposite to the voltage direction, we will get negative power. The same is for current source. We are comparing the direction of current source voltage and the value of this source. And also, if they are similar, we will get positive value. If they are opposite, we will get negative value. And the power balance equation, it is represented here. All consumers that we have, they always positive, and 2 types of sources, depending on the direction, could be positive or negative. But in any case, this power balance equation should be true for any system. And because it is transformation of energy conservation law, one of the fundamental physical laws. Then we discussed practical cases how we could apply this law. For example, application of Ohm law, depending on the type of branch. You could revise these practical cases if you forget something or want to discuss it more detail. All these examples are inside our methodical book. Also, here is example of application power balance equations, and then couple calculation in numbers, how to find the measurements, the value of measurement device, voltmeter for this case, or ampere meter or voltmeter in other case, how to make measurements inside electrical system. Voltmeter, generally, it is ideal measurement device or measurement device with infinity high value of internal resistivity. That is why for calculation, it could be substituted as an open circle, because through the voltmeter, current will not flow. Also, ampere meter is also ideal measurement device. The current through the ampere meter will pass, and the value of internal resistivity almost 0. That ampere meter shouldn't disturb the operation mode of our system. That is why voltmeter could be substituted as open circle, and ampere meter could be substituted as short circle. The next example was about finding the value of power inside system. And then we moved to such called combinations or equivalent transformations inside electrical system. It means that if we have combination of resistors or combination of sources, we could simplify the mathematical model by combining resistors in a single device to decrease the number of elements inside our model. It is called combinations or equivalent transformations. There are a couple cases of equivalent transformations. It is series connection, parallel connection, connection of sources. For example, here is represented in the case of serial connection, if we have resistors with the same current value on them, without any deviation, without any additional branches, all these resistances could be added one by one into one equivalent with the total amount of resistivity that equals the sum of previous resistors. Because according to the Kirkov law, voltage should be added in series connection, and all voltages is a multiplication of current and resistivity. That is why, because of same current value, the equivalent element should equal just a mathematical sum of all resistors. We see it here. In the same situation with active branch, if we have couple of sources, electromotive forces as source of voltage and resistors, the main restriction that the current value should be the same. The current should be the same inside each element. It is true if there is no additional branch in this system. If the current is the same, also we could add all sources, just depending on the direction, positive or negative, and we could add all resistors, just at the one amount as arithmetic sum of all previous elements. And instead of mathematical model with lots of elements, we could substitute the mathematical model only with two elements, one for sources, one for consumers. The same we could do for parallel connection. Because parallel connection, the voltage is the same, the current that inflow equals all currents that outflow. If we will write the total current that inflow as algebraic sum of current that outflow and substitute currents using the Ohm law as voltage divided on resistivity, we will obtain that the total resistivity in this case should be the sum of conductivities, the conductivity of total element here as opposite value for resistivity 1 over R equals all conductivities in each branch, 1 over R for each branch. Then for serial connection, we are adding resistivities as it's shown here. And for parallel connection, we are adding conductivities, the opposite value. Also, we discussed a couple of examples of equivalent transformation, how to find the appropriate values of resistivities between some points. If we have combination of elements, we're looking for resistivities between initial points, between points 1 and 1 with dot, 2 and 2 with dot, just having practice how to search it. And then we moved forward for the main methods, the main mathematical methods, how currents, voltages, and powers could be found in complex system when we have lots of elements. We have the main straight method, such called direct application of Kirkov's law, and mathematical transformation of this method in a couple of ways. The direct application of Kirchhoff's law, it is the simplest for understanding the simplest method, but mathematically it appears on the highest number equation that you could get, because in other methods they could be little harder for understanding, but all other methods will give you the smaller number equation at the first one. That is why generally in engineering practice, generally we use other methods as represented here. But what this method include inside? Because all these methods could be used further in sinusoidal current, and they are using further for any type of current source. That is why the main questions how this method should be transformed from direct current to other types of generators or types of electrical sources. That is why we are starting from them in direct current case. For the first method, direct application of Kirchhoff's law, we were describing that firstly, we are calculating how many currents do we have inside system. These currents will be unknown functions that we are looking for, unknown variables. In this example, we have 6 currents. As many currents do we have? As much equations we have to make to find these currents. If we have 6 unknown currents, then we have to make system from the 6 equations. How it could be reached? We are writing the second Kirchhoff law for the meshes, and we are writing first Kirchhoff law about currents for the nodes. As many nodes do we have, as much equations could be right, but the number smaller on 1. If we have 4 nodes, we could write 3 independently equation, and the last 4th equation will be dependent from the initial 3. If we have, for example, 6 nodes, then we could write 5 independent equations, and the last one will be dependent from them. I mean dependent mathematically. That is why for the nodes, we are writing the number of equations smaller on 1 than the number of nodes. Here, from the 4 nodes, we are writing 3 equations for currents. And then it is the first half of the system. And the second half, became from meshes. How many meshes do we have? As many voltage equations we will write. We have 3 meshes here and writing 3 voltage equations. It was in February on one of our lectures. Also, other example on the same idea to find currents. As we see here, we have 8 unknown currents, but also we have 1 current source. This current source will give a constant current in the branch number 8. That is why instead of 8 current, we have only 7 currents. That is mean we have to write 7 equations inside system to find these currents. Also, we are looking on the nodes. As we see, we have 5 different nodes. That is why we could write 5 minus 1, then 4 equations for currents, for Kirkov current law. It is written here. You could look on it at home, try to remember how we write this Kirkov current law. If will be any questions, please welcome. You could write me on email or in Telegram, and we will discuss it or personally or on the next class as you want. And also we are looking on the meshes, without current source, all meshes without current source. We have 3 such meshes, and it gives us other 3 equations for this system. As we see, 4 equations on the first current law, 3 equations on the second current law, and in total 7 equations to find the 7 currents in our mathematical model. For which object this model could be? It could be any object. It could be, for example, your house with different rooms or with different electronic devices inside it. For example, it could be a mathematical model of kitchen when you are trying to find the type of wire connections and calculate how electrical devices should be stored inside it. Or it could be some factory, or it could be some house with lots of flats, and you are calculating how these flats should be connected one by one and which power consumes each of them. It could be any object with power distribution inside it. And the ending of this example, the revision of power balance, just to check if we did everything right, if we calculate everything correctly. And then we transformed this method in different cases just to decrease the number of equations. The main idea was to decrease the number of equations. As we see here, for example, number 2, the number of equations became 7, and it is quite high amount, because if you don't have, for example, computer, or in any case, mathematically, it will be matrix 7 on 7, 7 rows, 7 columns. And if we could simplify it, definitely we should do it. That is why first variant of simplification, it called mesh method. We are dividing these 7 equations in 2 parts. First parts about nodes, and second parts about meshes. And one of method it is concentrated on mesh calculation, and it is called mesh method. And the second simplification concentrates on nodes, on currents inside nodes. And this is why it's called nodes method. First of them, the mesh method. The main idea, the substitution of real current that we are looking for into some imaginary value. We are substituting the real currents inside branches as some imaginary value mesh currents that is flow on whole mesh, on whole combination of branches. Then instead of 3 real currents, 1, 2, 3, for this example, we will calculate firstly 2 currents, 2 mesh currents, and it will decrease the number of equations instead of 3 into only 2. If we will write, let's see the whole picture. If we will write the Kirkov's law for this example on figure 5, we will get 3 equations, 1 for currents in the node, 2 for voltages inside meshes. And then we could make substitution for real currents into the imaginary, into the mesh currents. And instead of this initial system, we could write this one, inside which the unknown variables are currents, imaginary value of mesh currents. And it decreases the number of equations. Instead of 3, we get only 2. On previous classes, we were discussing how we are doing it, how we should make this system. You could just read this once more time and look on it more detail. If it will be necessary, also you did it on practice with teacher Ludmila. If you will have any questions, please welcome. If some of these parts should be revised, please write me and we will discuss it more detail on the next classes. But I think the general ideas should be okay because we worked with them previously. Couple of examples in numbers. For 2 sources, 3 consumers, finding the mesh currents 1 and 2, make an equation, solve this equation, finding currents, and check them by power balance. Also, for more complex system, with 4 meshes, we have 4 equations in total. The last mesh just equals the current source. And for this system, we are looking for 3 unknown mesh currents, first, second, and third. Then, after we find mesh currents with double index, we are finding the real currents with single index, just the real currents that flows in our branches. And then we moved to the second method, concentrated on nodes. As you see here, all equations connected only for voltages, and we are describing only voltages inside meshes. If we will move to Kirkov law, the general method. Here it is. For mesh method, we were working only with voltage part of equation. But for the next method, we will work only with current part of equation. Currents inside nodes. Let's move further. It's called node method, node analysis method. And the main idea for each node that you have, transform the current equation to obtain some system. Here it is. For each node, we are writing what current do we have for first and second node. This current could be rewritten as a potentials and conductivities. And on the last step, we will obtain only two equations dependently from these potentials, these conductivities, and current sources. Also, here it is algorithm, how it could be made, starting from which ideas we should write the system of potential equations inside nodes, and examples how it could be done. For example, here with two sources, 4 resistors. First step, we are pointing the potential point, first, second, and the total third, because between left and right point, there is no element. That is why left and right point is the same point number 3. Then, after we put the number of nodes that we are searching for, we are making some grounding. We are assuming that some point equal 0. And starting from this 0 point, we are searching for other two, point number 1 and point number 2. Our final goal to find the potential first and second. After we found it, we could find all currents in this system. How we are doing it? For the first point, we are making the necessary equation. Here it is. Potential multiply on all conductivities connected to this first point, minus second point and mutual conductivity between these 2 points, and equals inflowing current to this first point, and this inflow current equals electromotive force multiply on conductivity of this branch. It is how we made the first equation. The second equation, we are doing using the same idea that we have. Just one moment. We'll decrease scale that. Okay.
Professor?
Okay. Yeah.
How do we know the sign of the phi1 and phi2 and phi3? How did we know that phi1 minus phi3, not phi3 minus phi1?
Nice question. For the voltage, we always minusing the second index from the first. If we write voltage 1, 3, that is mean we are taking first minus third. If we are writing 2, 3, it equals second minus third for any voltage. For example, if we will write voltage 3, 1, it will be third minus first. And it will be opposite value to 1, 3. And this index, they identify their direction of voltage. For example, 3, 1, it is voltage from point 3 to point 1. Voltage 2, 3, it is direction from point 2 to point 3. Here it is. Okay?
Okay.
Okay. Yeah, thank you for your question. Then our main goal to write the voltage equation for this, write the current equation to this mathematical model. And for the second node, for phi2, we also writing the value of this potential on conductivities near this point. Conductivity, I will show it. Conductivity through R2, through R5, and it should be conductivity through current source, but the conductivity of current source equals 0, because for this element, the resistivity is very high. That is why we don't take it into account and only taking resistors. The own conductivity as 1 over R2 and 1 over R5, and minus, always with minus, the other point with mutual conductivity between point first and 2. When we are writing equations, we always take in with minus all other values. Just one moment. Let's see it here. If we have some system, I will go only in general case without resistors, just as a topological view, just as a general scheme. For example, we have a system of some potentials. And if we are writing equation for the first one, it always taken with plus. But all other always is taken with minus. As you see, all other potentials are taken with minus. Then we are moving for the second equation, for the second potential. And this value also will be with plus. And all other should be with minus. It is a general mathematical idea of this method. And so on and so on. For all other potential, for the third one, for example, the third one will be with plus, all other will be with minus. The last one will be with plus, the last one will be with plus, all other will be with minuses. That is how we are making this system. About currents, the right part, it could be or positive or negative, depending on the direction. If source of energy oriented to some point, it will be positive. For example, if we are writing equation near second point, and we see that this source oriented to this point, then the sign will be positive. If, for example, we have some source oriented opposite of this point, then this source will be with minus. We are looking just on the direction, comparing with the point for which we are making equation. And for this example, after we make for node number 1 and node number 2 two equations, obtained system, we are substituting number of resistors, substituting number of sources from the initial condition, from the initial data. And after it, solving this system of equation, we will get the potential values. Two potentials in this system. After we get it, we could find all currents. If we know all potentials, 0, 20 volts, and 40 volts, starting from them, we could find all currents. For example, for current number 1, we see that it lies between potential first and third. Also, one source of energy present here. The direction of source of energy is opposite to the current. Then in upper part of Ohm law, we are writing these voltages, Phi1 minus Phi3 minus E1, and the value of resistor. Divide on the value of resistor. As we see in upper part, we obtain 0 voltage. That is mean that the first current also equals 0. It just disappears because total voltage disappears in this branch. But in the next one, in the second branch, the current appear. It equals Phi2 minus Phi1. We always taking the point from which current starts minus the point in which current ends. Looking on the current direction. And here it will be 40 minus 20 on the voltage divided on 10 equals 2 amperes. The third current equals only source, 4 ampere. And fourth and fifth current, and the potential difference, current number 4, first potential minus third, current number 5, second potential minus third. All current value as 2 amperes. And we could check it on power balance. If everything is okay, just obtain power balance for sources, power balance for consumers. If they are equal, then we find everything okay. Also, we could check it on the value of current. If you see current first equals 0, current second equals 2, current third equals 4 as value of source, here is 2, here is 2. And everything is okay because current 4 ampere, as we see, divide on 2 plus 2. And then this 2 only goes on central branch without flowing on the resistor R1. Check it by number and see that everything that we found is okay. Check power balance and see that it is true. And the next example only makes once more the same idea how to find currents from the potential equations and how we should make nodal equation for this case, for this mathematical model. I think for today, it was lots of information. I think for today it's enough. If you have any question, please welcome. You could ask anything if you want. If no, just thank you for your attention. Wish you a nice day. And if revision material or looking this video once more or just reading books at home, if you will have any questions, please welcome. You could text me in Telegram or text me on the email.
Okay.